it's Michael. Good morning, everyone. Today we continue our discussion. And today we'll be discussing about oxygen dissociation curve of fetal hemoglobin as well as the Bohr effect. Now this fetal hemoglobin oxygen dissociation curve, is the percentage saturation of fetal hemoglobin with oxygen at various partial pressure of oxygen. Now fetal hemoglobin HbF, which is termed as HbF, is the main oxygen carrier protein in the human fetus. Fetal hemoglobin transport oxygen from the mother's bloodstream to organs and tissues in the fetus. Right now, oxygen diffuses from the mother's blood into the placenta, then into the fetal's blood. And apparently there are three factors that allow this oxygen to pass from the maternal circulation into the fetal circulation. So let's discuss these three factors first before we proceed with the curve. So the first factor is the presence of the hemoglobin F in the fetus allows a stronger binding to oxygen than maternal hemoglobin. Now hemoglobin F is apparently the gamma, the sets of gamma chain that can be found in the fetal hemoglobin. Take note that adults hemoglobin consists of a set of alpha chain as well as a set of beta chain. While the fetus hemoglobin consists of a set of alpha chain as well as a set of gamma chain. Right? That set of gamma chain cause the fetal hemoglobin to have a stronger binding of the fetal hemoglobin with the oxygen. So meaning to say fetal hemoglobin has higher affinity for the oxygen compared with the adult or maternal hemoglobin. The mother's bloodstream is richer in oxygen apparently. So meaning to say the mother's bloodstream has higher partial pressure of oxygen than the fetus. So oxygen will naturally flow towards the fetal circulation by diffusion. And then the effects of pH on maternal and fetal hemoglobin. Now, as the maternal blood acquires more carbon dioxide, the maternal's blood becomes more acidic, because of the increases of the hydrogen ions. And this favors the release of oxygen by the maternal hemoglobin. I think up to this extent you know already why when there is an increase of hydrogen ions in the blood, it will cause the release of oxygen from the oxyhemoglobin. At the same time, the decrease in carbon dioxide in fetal blood makes the fetal blood more alkaline and favors the uptake of the oxygen. Now this is the oxygen dissociation curve of the fetal hemoglobin, incomparable with the adult hemoglobin or the maternal hemoglobin. Now from this graph, you can see that the curve which referring to the fetal hemoglobin is to the left of the adult hemoglobin. Right now, this shows that the fetal hemoglobin is easily saturated with oxygen at low partial pressure of oxygen. You can see from here, right, at P50, let me get my pointer. At P50 means at half of the percentage saturation of hemoglobin at P50, is achieved by the fetal hemoglobin at around 4 kilopascal of partial pressure, compared with the adult hemoglobin, which is at 5 kilopascal partial pressure of oxygen. So the fetal hemoglobin has higher affinity for oxygen than the adult hemoglobin. Now this is important for the fetal hemoglobin to transport oxygen efficiently to the fetus. Alright, now that's about oxygen dissociation curve of the fetal hemoglobin. Now let's continue with the Bohr effect, which is related. Okay. Now, Bohr effect is a process, okay, where affinity of hemoglobin towards oxygen is reduced, and the oxygen dissociation curve of hemoglobin is shifted to the right. Now, you know that when the oxygen dissociation curve of hemoglobin is shifted to the right, it means easier for oxygen to be released from the hemoglobin. Okay, easier unloading of oxygen from the hemoglobin. Now, this Bohr effect is caused by carbon dioxide, okay, which is given out by active respiring cells. Increase of carbon dioxide will decrease pH of the blood, right? Because you know carbon dioxide will diffuses into the red blood cell, okay, which it will combine with water, to form carbonic acid, which is catalyzed by the carbonic anhydrase. This carbonic acid is unstable and dissociates into hydrogen ions and hydrogen carbonate ions. That hydrogen ions, okay, which in turn will cause, okay, the decrease of the blood pH. Lower pH, okay, of the blood will cause the hemoglobin easily unloads its oxygen. Okay, and as what I've explained in my earlier video, okay, the oxyhemoglobin will unload the oxygen, and the deoxyhemoglobin, okay, will combine or binds with the hydrogen ions to form hemoglobinic acids. Okay, now this is a graph, okay, that tells you a Bohr effect examples. Okay, now from this graph, okay, you can see 50% hemoglobin saturation, okay, with oxygen can occur although the partial pressure of oxygen is more than 5 kilopascal. Okay, so the Bohr effect causes the hemoglobin to have lower affinity for oxygen. Okay, now let's say without the Bohr effect, this is the original hemoglobin curve. Okay, sorry, this is the original oxygen dissociation curve of the hemoglobin. Okay, at P50 can only be achieved at lower than 5 kilopascal partial pressure of oxygen. Okay, but what happens, P50 can be achieved, or 50% oxygen saturated with hemoglobin, 50% hemoglobin saturation with oxygen can be achieved, okay, although the partial pressure of oxygen is higher than 5 kilopascal, okay, with Bohr effect. Without Bohr effect, which is quite impossible, okay, P50 can only be achieved at lower partial pressure of oxygen. Okay, I believe you have that understanding from the earlier part of our video. Okay, now why this Bohr effect is important? Okay, it causes the hemoglobin to have a lower affinity for oxygen. Okay, so that hemoglobin can easily unload its oxygen, okay, that will diffuse into the active respiring cells. You know that active respiring cells gives out carbon dioxide and takes in oxygen. They need oxygen, so the oxygen can be readily available, okay, from the oxyhemoglobin because of this Bohr effect. And then this Bohr effect also increases oxygen supply to the fetus. Now, apart from that, okay, homeostasis control. Okay, Bohr effect also contributes to homeostasis control in our body. How? Okay, by maintaining our blood that is close to neutral, as close to the neutral as possible. Okay, although there is a high partial pressure of carbon dioxide, because the hydrogen ions from the blood is removed by binding with hemoglobin to form hemoglobinic acids. So this prevents Okay, not prevent. This cause our blood pH to be close to the neutral. That's why no matter how strenuous exercise you do, your blood doesn't get acidic. It's still maintained close to neutral, right? So that's it for today. Okay, so any issues with the lectures, please comment or you can email me. All right, thank you. Bye.